Okay, hi everyone. So I'm not going to talk about anything related to Mobileye today. Instead, I'm going to talk about somewhat new company called Mentee Robotics, founded by Amnon Shashua, Lior Wolf, and myself about 2 years ago, where the goal is to build a humanoid robot. But let me start with the exciting times that we are living. Everyone that is working on AI sees that these are really amazing times. And this is the background for our work on humanoid robots. So in the last 25 years, we see 6 revolutions in AI, where 4 of them is in the last 5 or 6 years. So everything is accelerating. The revolutions are machine learning revolution, deep learning revolution, generative pre-trained transformer, or with the acronym GPT, which is very well known, consolidation revolution, reasoning revolution, and the sim-to-real revolution. And all of these are the background for what we are doing in Mentee Robotics and why we think now is the right time to solve the problem of humanoid robots. So before the revolution, I was an undergrad student at the Hebrew University, and I was working part-time at a small startup designing classical AI computer vision systems for detecting ellipses in images in order to find information on for pregnant women. And everything was code-based, and there was no machine learning and no AI and nothing. This was just 25 years ago or less. Then in 2010, I joined Mobileye as an advisor. And all the systems at Mobileye were shifting from manual coding to systems that are based on machine learning algorithms. Back at the time, it was mainly support vector machines and AdaBoost on hand-tuned features. So still, people were thinking hard on what are the right representations or features of images. And then given the right representation or the features, their combination was something that was learned out of data. And then 2 years later came the deep learning revolution, which is the second revolution here. Instead of hand-tuned features, let us learn the features as well, which is what the famous Krzyzewski-Sutskever-Hinton 2012 paper showed. The ideas were there before that, but they showed that it gives a big jump in performance on the image in a data set. And at Mobileye, we shifted all the technology to rely on deep networks. And we were the first to deploy deep networks on an embedded system on an IQ3 chips. The IQ chips are the chips that we developed at Mobileye, and it was in production on the first generation of the Tesla Autopilot in 2014. So again, we see very, very quickly how technology, which we worked on for 10 years or more, is being replaced by new one, better one, very, very quickly. Then came the GPT revolution. GPT is generative pre-trained transformers. Before the GPT revolution, basically deep learning was very, very successful. When you had the resources and the time, you were a big company, you could collect many, many examples of what you want to learn. So for example, in Mobileye, we had big data sets where we had images and we had people that manually labeled on each image. Here is a box in which there is a car or a pedestrian or something else. And once you do all this stuff and work very hard on creating this data set, then you had data, labeled data, and you can apply supervised learning algorithms where you show the machine learning algorithm, you showed it images, you showed it what you want to find in the images, like boxes around images or boxes around pedestrians, and then it figures out how to do it. But then in 2019, I was joining AI21 Lab, a company that aimed at doing work on rephrasing. So things like you have this sentence, this opportunity interests me, and then the system proposes rephrasing of this sentence. And if you think about coming up with a lot of labeled data for this task, it's very complicated. There is no ground truth, there is no clear truth about what is the answer of what is a good rephrasing. There are more than one possible answer. It's a matter of taste a little bit, and it's very hard to collect a lot of data for this task. Came the GPT revolution, generative model, which were pre-trained on the internet in a self-supervised manner, so no labels, simply learn to predict the future and figures out the distribution of data over the internet. Later, in context learning, you explain the task to the model, and the model is supposed to perform it. So basically, there is a sequence of tokens. Think about it as word, T1 to Tn, and the model learns to predict the next word given the context, given the previous words. Later on, after you learn this model on a lot of data, then either by zero shot, one shot, few shot, you show instruction to the model or some examples, very few examples, and the model needs to figure out from the general understanding of what it's doing, what exactly you want it to do right now. So this was also a big revolution. But then came more, the consolidated revolution. So when I started to work on machine learning, there were different experts on computer vision, voice understanding, speech understanding, natural language processing. Each one of these scientific fields had its own conferences. People from NLP couldn't speak and understand people from speech recognition or from computer vision. They all had different methodologies, different tools, and different approaches to solve their problems. Today, all of these fields are dominated by deep learning. You can do NLP and computer vision and speech understanding and many other tasks by exactly the exact same techniques, and moreover, even the architecture of the neural networks that are being used is consolidated together into very few architectures like the transformer and maybe few more. So this consolidation is also very critical and is a revolution because it enables us to work on multimodal problems. So jointly understanding speech and images and language all with the same technique. Now it's possible. Next came the reasoning revolution. For many years, reasoning is maybe the holy grail of AI. We did learning for a long time. What's the difference between learning and reasoning? So in a sense, learning is to compile a compact rule out of given observations. So basically to find the compact rules that explains what you see. Think about Occam razor. And reasoning is expand outside of the knowledge of what you saw. So you saw examples of some phenomenon. In reasoning, you want to understand things that you never saw before. So to go outside of the boundaries of your knowledge. And these days, we are in the phase of the reasoning revolution. This is taken from Alexander Wang. A very nice image that illustrates that there was the famous paper of attention is all you need that started these models, BERT, then came GPT. Then there was a second phase of scaling in which these models became larger and larger and larger, and the mere fact that they became larger gave them a lot of power. But then we see a glass ceiling of continue to enlarge these models. Basically, we are out of data. And now we are in the phase of the third component maybe of what's going on in AI, in which models are starting to reason about things. And when they are reason about things, they go outside of the knowledge of what they saw, that they are able to solve things that they didn't see in the training set. The sixth revolution is a sim-to-real revolution, and this is the main thing that I would like to talk about today. And basically, when we think about learning, there are two paradigms of learning. There is learning from data, supervised learning, unsupervised learning. Basically, you see observation, you see data, and you need to figure out something out of the data. And there is a second paradigm of learning, which is called learning from experience, in which you want to try something out, fail, succeed, gain some reward of what are the failures and what are the success stories, improve yourself, try again, sometimes you fail, sometimes you succeed, try again, until you figure out what to do. And the best examples that I have for why learning from experience is important, think about learning how to shave. It's not a good idea to learn how to shave by watching YouTube videos, okay? You want to try it out a little bit. So this is learning from experience. Now, learning from experience is something which is not new. The problem is that when you are talking about learning from experience in the real world, we have a problem with the real world. The real world has two issues. First, it is very slow relatively to the cyber world. So when we train GPT on the entire internet, we are doing it much faster than our ability to train a robot to do some task, because with robots, we are limited by the physics, by the natural flow of time. So reality is slow. Also, reality is dangerous. There are some tasks that, you don't want to fail too much in reality. Sometimes it's okay, sometimes it's very bad. If we're talking about autonomous driving, you don't want to fail in autonomous driving. So these are problems with reality. What can be a solution for this? Simulation. If we can go back to the place that we like, the cyber world, and learn in simulation, it's great. But then we have a problem. Maybe we learned something in the simulation and we have a distribution drift. Once we switch from simulation to the real world, then things are not working anymore because of slight deviation from simulation and reality. And this is called the sim-to-real problem. And recently there are new ways to overcome the sim-to-real problem and train things in simulation, apply them in the real world, and it works. So I will elaborate a little bit how it is being done. But before that, what we did with it, so at Mentee, we took the problem of building humanoid robots with an AI-first approach. So the idea is that we want that the robot will be built, designed, and all aspects of it will be based on AI, as opposed from classical control theory and model-based approaches. So I will show you a short video showing what we have today. This is version 2 of the robots that we have today. It still doesn't look very nice, the robot, but it can do pretty interesting things. So what you will see is a demonstration in which one of our employees giving the robots instructions of go to somewhere and do something, and the robot understands the instruction, so understand voice, can navigate its way in the world, can control itself and not fall. Okay, so we have here language understanding, speech understanding, computer vision in order to navigate its way, then do some tasks, and all of that consolidated by a single AI machine. So
what would you like me to do?
Hey Mentee, please go to the table in the kitchen and wait for instructions.
Okay, I will go to the table in the kitchen.
So I'm pausing it for a moment. So the robot already now had to figure out many things. First, understand the voice, translate it to text, then figure out what is the instruction, what to do with this text. In addition, the robot has a cognitive map of the office. You can see it on the left side over there. So it knows where it is in the office, and it understands what is the kitchen, okay? By the way, understanding where is the kitchen is something that the robot figures out by itself. So it is based on models, vision models, and language models. So it knows once it mapped the office, it knows where the kitchen is. So it builds a map and also understand, you can say the kitchen, but you can use other words and the robot will understand it. Now we also see how the robot walks. So all the walking of this robot was fully trained by reinforcement learning in a simulation and then translated to the real world. I will pause it again. The robot needs to figure out that it arrives to the right position, okay? So it needs also to constantly monitoring what is the state of the robot, and then it will give feedback to the human that, okay, I'm here, what to do next?
I have arrived. What should I do now?
Please put the fruits in the container and place it on the counter behind you.
Sure.
So now he got a composite instruction to take the fruits, put it in the container, and then move the container to some other place. So again, it needs to break it into several subtasks and perform the tasks. The robot needs to understand that only after he picked up the container, he can start working to the other location.
Thank you, Mentee.
So here you see that the amount of tasks that needs to be done, even for such a simple demonstration, is really overwhelming. There are so many things that needs to be coordinated together. And it's very complicated to build such a task, but only with AI, with consolidation, with relying on all the assets that came in AI in the last years, such a task can be achieved. The robot that you saw is our first, it's actually version 2, and what you see here is version 3. It looks much nicer, more sleek. It also has detachable batteries. So what you see now is that the battery was taken out of the robot, and the new one is placed on the robot. It has a small second battery, so this allows the robot to continue work for 24 hours without any break, okay? Because just swapping batteries and continue charging the other batteries, everything works while the robot is still on. Okay, so what is behind the sim? We have reinforcement learning plus sim-to-real for locomotion. So there is a deep neural network for the robot policy, which translates the state of the robot to action. The state is proprioceptive information at high frequency. Basically what we can take out of the engines and also of the motors and also IMU. as well as some high-level information from vision sensors at low frequencies, such as existence of either navigation information or existence of stairs or obstacles on the way. And the action is the desired position, angles, and velocity of all the joints. And on top of it, we have a classic controller in order to move, to give currency to the motors in order to move the angles of the joints to the right position. The training is performed on a simulator and is applied to the real robot using sim-to-real technique. So what is the sim-to-real problem? So basically, we have a physics simulator. There is a description of the state. There is an action that the robot is doing. And then in the simulator, there is a next state. But in reality, next state will not be exactly the next state. It will be something else. And the gap between the next step in the simulator and the next step in reality is the sim-to-real gap. And this gap is because all of the small things that we are not modeling good enough in the simulator, friction and other stuff. So how can we overcome sim-to-real gap? There are basically three approaches. And we are doing all the three. One approach is improving the simulator. So the better the simulator, the smaller the sim-to-real gap. What you can do? One thing is use learning again. So we use supervised and unsupervised learning in order to find parameters of the simulator in order to model our actuators better and better using learning. So this is one thing. Secondly, tight hardware and software integration, and we design our own actuator in a way that will minimize the sim-to-real gap. This is one of the design choices in building our own actuators. The second approach is to be robust to the gap. Basically, all sorts of smart randomization that we add in the simulation so that the policy that the reinforcement learning figures out can handle a large amount of noise, and by handling a larger amount of noise, it gives robustness as to the sim-to-real gap. And third is to adjust the policy to the gap. It's something that is called in the literature sim-to-real to sim adapter. It's basically in simulator, we have something that moves the physics by something that is learnable and aim to understand the gap. But in reality, we're not applying this adapter. So just to give you a glimpse of what we design ourselves, so the power distribution unit, the motor controller, communication board, the actuator design, and the motors themselves, and the Jetson carrier board, all of this we are developing ourselves, again, in order to minimize the sim-to-real problems. By doing this, we have a good control on all the components of our solution and of our robot, and then we can add them into the simulator, which allows us to train the robot in the simulator. So why now is the right time to talk about humanoid robot? Because a key ingredient is there. We have large language models in order to understand the instruction, in order to break a problem into sub-problems. All of this is in the LLM arenas. We also have very good simulation to the real world, both sim-to-real. We can train in simulation and deploy in the real world. Visual and large language model combination, so we can have models that know the position of the kitchen, okay, in the videos that I showed you. So by visual and language, and know the connection between what the robot see and what is the verbal meaning of what it see. What is a counter? What is a fruit? What is a container? All of this, talking with language and translating it into the computer vision is something that we have with the consolidation revolution. And finally, the hardware and compute. We have nowadays we have very strong on-device computers. So all of this is great, but something is still missing. And what is missing is our vision. Mentee's vision is to enable humans to mentor a robot. This is why we call the company Mentee. We want to teach the robot to perform a new task by either a textual instruction or by a human that demonstrates a task to the robot. So a human is standing next to the robot is standing next to it, next to the human performs some task, explain what he is doing, and we want the robot to look at it from the side, understand the task, understand what it needs to do, and then be able to perform it. This is a vision. This is what we want to achieve. So it's, if you can think about it as an analog of instruct prompting and few-shot learning from the ChatGPT and LLM arena, where you can explain the model what you want it to do, and in many of the times, the model understands what you want it to do and perform it. But this happens with text only. Now we want to do it in robotics. So we need a foundation model for robots. And this is something that we took from Twitter, from someone by the name of Ashish Kapoor. Basically, he made a very nice comparison between what happens in AI and what happens in robotics. So in AI, we have companies like OpenAI, where the approach is supervised fine-tuning with RLHF. RLHF is reinforcement learning with human feedback. So how we align a large language model to perform some task. We collect a lot of data. We have humans manually annotate this data, give it a reward. This is better than that. And we collect a lot of data, and then we align the model by some iterations of reinforcement learning of this manually labeled data. DeepSeek, on the other hand, a Chinese company, did it completely by reinforcement learning. Basically says, let's minimize the amount of human labeling and rely more and more on reinforcement learning. Now in robotics, we have companies like Pi, Tesla, Figure AI, all of these companies trying to mimic the same things that OpenAI are doing, basically have human demonstrating tasks to a robot, and then they want to build foundation models that learn how to perform tasks based on this data. But what is really missing is how to do it with reinforcement learning while minimizing human supervision. And this is a way to scale in robotics. Now, if you think about teleoperation, human teleoperation, and learning from human teleoperation, then this is something that is very successful in autonomous driving. So some companies say, let's do the same with robotics. But there are several delicate differences between autonomous driving and humanoid robots. First, the number of tasks. In autonomous vehicles, there are not so many tasks that a car needs to do, while in humanoid robots, it's open-ended. In addition, the variability of design and sensors of autonomous cars is not high, while in robots it's high. All cars look the same, don't be offended. There is also the difficulty of data collection. If we want to do data collection, we simply put a driver in a car and the driver collects data. But for humanoid robots, what we do, so there are suits that, human put suits and VR glasses, and then it performs the task, and the robot performs the same. So this is how data collection is being done. It's very cumbersome, it's very expensive, it's not scalable. And finally, the data availability for driving is huge, and for humanoid robots is very small. So our approach instead is to train a foundation model on a simulator and rely on sim-to-real technology. So basically, we want to minimize the human supervision by relying on a RL. So we start with a task in a simulator. We solve it by reinforcement learning without human intervention. We don't need the human intervention. But this solution in the simulator then used as data for imitation learning in order to learn a foundation model for many tasks. So we support various forms of instruction, side view, where the robot is on the side, look at a demonstration of a human, textual instruction, and this approach is robust to different actuators, sensor position of the robots relatively to the human. And finally, you need strong sim-to-real in order to take the foundation model that you learned in the simulator and translate it into the real world. So the architecture of the foundation model that we are building is something like the following. So we have frozen weights. Some component of the deep network is with frozen weights, and this is mainly for the sim-to-real gap. and some are learnable. So we start with language encoder, vision encoder, which are with frozen weights. These were learned on ton of data over the internet. And then we feed text instruction. We feed images from the ego perspective of the robot, so from the cameras that are on the robot. Also images from side view for cameras that are on the side to mimic something that a human performs some task and the robot observes it from the side. And of course, we take the proprioceptive info of the specific robot and also encode it by a multi-layer perceptron. All of this is into a big encoder that should understand the thing, a cross-attention encoder, and then a diffusion-based decoder that gives a sequence of actions for the robots to perform. So all of this is learned together in the simulator, and we obtain sim-to-real capabilities because all the sensor information, text and vision, are frozen weights. So it looks the same in simulator and in reality because these models were trained heavily on real-world data. The proprioceptive info is not the same in simulator, but we know how to have adjustment. This is our sim-to-real technique. And then all of this is learned together in order to give a big architecture that is learned to perform many, many types of tasks. So to sum up, physical AI is AI in the physical world. For physical AI, learning from data is insufficient, like learning to shave. You need to try it out. You don't just look at other people shaving. You need learning from experience, but learning from experience in the real world is not scalable. So the solution is to perform large-scale learning in the simulation and combine it with sim-to-real techniques. So our approach, our AI-first approach to humanoid robots is to leverage learning from data for language, vision, and voice understanding. So all of this is a very good fit for the learning from data. We leverage learning from experience in simulation for data efficiency, and then bridge the sim-to-real gap by designing of our own hardware and tight software and hardware integration, learn the gap, and own the gap by being robust to the gap. Thank you very much.